Hello everyone. So today we'll be looking at the history of the atomic model. We're gonna see that how the atom evolved. We're gonna look at how it just started off as a particle, a small ball, into this complex junctions of electrons, protons, neutrons, and probability waves and all that. We're also going to look at a few key experiments, such as the goldfoil experiment, and we're also going to look at why some theories were accepted and why some theories were declined, and the pros and cons with most of the theories and models that were put forward. So without further ado, let's just get straight into the video, starting off with the first atomic model, and that was the solid Bohr model. Now the solid Bohr model was proposed by Democritus, a Greek philosopher. So basically, before Democritus, people believed that matter was made of four key elements: earth, fire, air, and water. Now, they also believed that matter was continuous. So this is a key term, continuous. So what does continuous mean? Well, continuous basically means that, for example, if I have this marker, I can cut it in half, and then I can take that quarter, and then I can cut it in half, and I can cut it, and I can keep cutting this marker into smaller pieces forever. And I can never stop, it always gets smaller. However, Democritus suggested that matter was not continuous. So he broke the old perception that matter was continuous. He said matter was not continuous. Instead, he said that matter was not continuous. So he already said that, and he said it could be broken down into tiny indivisible particles. So we could say that matter was not continuous, but could be broken down into tiny indivisible particles. And this tiny indivisible particles is what atomos means. So this portion is atomos, and that's where the name atom comes from. So this is the first solid Bohr model that was presented by Democritus, and the model before that, the one that said matter was continuous, was presented by the Greek philosopher Aristotle. So we had the first theory, which is the solid Bohr model, and then around about 2,000 years later, 2,400, something like that, came Dalton's model. So now let's take a look at Dalton's model. Okay, first of all, Dalton confirmed the solid Bohr model. So he said everything about the solid Bohr model was correct. But upon this, he added three other key points. And first of all, he said that atoms of different elements are different. So, for example, imagine that you have a piece of gold and then a piece of carbon. Now, if you were to take those pieces and find their atoms, so if you have a piece of gold and if you have a piece of carbon, then you cut down to each of their atoms, they're going to be different in some way. Dalton didn't exactly explain how they would be different, although now we know it's the number of protons. He didn't exactly explain how they were different. He just said that different elements have different atoms. Another thing he said, that these atoms can combine in specific proportions to form compounds. So imagine I have a hydrogen. Imagine I have two hydrogen atoms, and an oxygen atom. So that's a specific proportion where the ratio of hydrogen and oxygen atoms are 2 to 1. So, and let's say I combine them. And I'm doing it in a specific proportion, 2 hydrogen for 1 oxygen. And that forms a compound. So 2 hydrogen, H2, 1 oxygen, H2O. That's a compound, that's a molecule, which is an example of Dalton's second key point that he raised. Now the third key point that he raised was all atoms of the same element are exactly alike. So imagine that we have 2 pieces of pure gold. We cut down to their smallest piece of matter, which is an atom. Now if we compare the first piece of gold's smallest atom is atom, and the second piece is atom, they're going to be exactly alike. Alright, so then this was Dalton's model. After Dalton came jjthomson, who came up with the Plum-pudding model. So now let's take a look at jjthomson's Plum-pudding model. So, this was proposed in 1904. Okay, so the story starts with jjthomson conducting the cathode ray tube experiment. Conducts the Then he discovers the electron. Now back then he didn't call it electron, he called it something else. He called it corpuscles, although the electron was discovered by him. So if asked who discovered the electron, we can say jjthomson did. But at the time when he did, he didn't necessarily call them electrons, he called them corpuscles. Alright, so he discovered that there was negative charge in an atom. So if there was a negative charge in the atom, negative charge in the atom, there must also be some form of positive charge. Hence ensuring that the atom remains neutral. Alright, so jjthomson, he put his model something like this. So he said that if this was my atom, just a ball, this is Democritus' solid ball model. Atoms are made of small balls. This is his ball, right? Then what jjthomson said is, on that ball, let's imagine this is a pudding, not a ball. On that pudding, there's going to be small spots of plum. And these small spots are going to be our electrons. Now he said there also must be a ball of positive charge to make sure that the atom remains neutral. So this entire ball, this entire bigger ball is positive charge. So according to jjthomson's model, an atom was a ball of positive charge with smaller electrons attached to it, similar to how plums can be seen in a pudding. Now remember, back then the proton wasn't invented, so he only merely referred to this positive charge as a positive charge. So if asked to describe the model, don't straight jump in and say there's a proton with smaller electrons attached onto it, because protons were not discovered. You can use the term electrons, but please don't use the term protons, because they weren't discovered then. Okay, and then after J.J. Thomson's plum pudding model came Ernest Rutherford's nuclear model, and this is where the goldfoil experiment kicks in. And so firstly, to understand the nuclear model in much more detail, Rutherford's model in much more detail, we're going to look at the goldfoil experiment. Okay, so firstly, let's take a look at the goldfoil experiment. Now, how was the goldfoil experiment set up? We're just going to go straight into the key aspects of it. So, set up something like this. Alright, so there was this box, which was the source of alpha particles. And what are alpha particles? They're helium nuclei. And what is a helium nuclei? Two neutrons and two protons. So a helium nuclei is basically a positively charged ball. So we can just imagine them as positively charged balls. And now what this box did is that it shot helium nuclei towards this. This is a thin sheet of gold foil. Okay, and then finally there was this fluorescent screen. Basically what this fluorescent screen would do is that as these helium nuclei, as these alpha particles came through and they went through this, they interacted with this gold foil, they'd go pretty much somewhere along here, and what the fluorescent screen did is that it picked up where the alpha particles went. So if the alpha particle, for example, hit this portion of the fluorescent screen, this portion would light up. There would be a small spark over here. So when they did this experiment, so what they found was that they shot the alpha particles, and most of them went through quite easily. Most of the particles, nearly all of them, they went through quite easily. And then some of the particles, so what they did was that they shot these, and then they found where the lights came on the fluorescent screen. And what they found is that most of the light came up over here. It went straight through, penetrated straight through the thin sheet of gold foil. And remember, a thin sheet of gold foil, we're talking really thin, only a few atoms thick. So here you're probably only dealing with like a width of like 10, 12, probably even less than that. That's the width of this thin sheet of gold foil. So we're not dealing with like markers or piece of paper, even thinner than a piece of paper, than the width of a piece of paper. So what they found was that most of the alpha particles went straight through. They found that some were slightly deflected, and they thought this was probably just some form of error. But then they found that a few of them were just completely deflected. Now, how could this be possible? So this is what they were expecting to see. This is what they got as well, but they only assumed that, okay, well, look, it's just probably a few errors here and there. But then why were some of these just completely deflected? So the Plum pudding model only supported the idea that the alpha particles go straight through. It could not explain the small deflections and the complete reflections, which is why they decided to scrap the Plum pudding model. And after this, Rutherford gave his hypothesis. So let's look at Rutherford's hypothesis. That this diagram is showing you the results of the experiment. Okay, so now let's look at Rutherford's hypothesis. So he looked at the results, and then he's like, okay, so what do we understand from this, and what can we draw about the model of the atom from what we have just seen over here? Now, firstly, we saw that most of the atoms went straight through. They penetrated just straight through. So from that, Rutherford concluded that most of an atom is empty space. And why is most of the atom only empty space? Because most of the alpha particles penetrated straight through. Okay, now the second piece of hypothesis that he came up with is that there's a small dense ball of positive charge located in the middle of the atom, known as the nucleus, as a small amount of the positively charged particles were reflected and somewhat deflected. So he said that most of an atom is empty space. So let's kind of try and visualize that, right? So let's say this is the space that we're giving to an atom. This is the space that we're giving to our atom. And so if this is the entire space that our atom occupies, most of it's going to be empty space. And then he said that there is a small dense ball of positive charge known as the nucleus. Remember, he does not talk about protons here yet. Sorry, he doesn't talk about neutrons here yet, because we don't know about neutrons. Neutrons were discovered by James Chadwick a bit later on. So firstly, he just says, okay, look, there's a small dense ball of positive charge. And why is that? Because if we go back to how the alpha particles were reflected, remember the alpha particles are positive. And so the alpha particles were reflected. And why were they reflected? Because positives and positives reflect. So when a positively charged alpha particle came in, most of them just went straight through because none of them could hit, only a small amount could hit the nucleus. But the very few that did hit the nucleus, because both the alpha particles and the nucleus were both positively charged, this got reflected, or if it was to hit it if the alpha particles were to hit it at an angle, they got deflected. And so that's why his second point comes. There's a small dense ball. There's a small ball in the middle of the atom, known as the nucleus. As a small amount of the positively were deflected, or okay. Now, from jjthomson's model, we know that, okay, if there's positive charge, there also must be negative charge, because that's what makes an atom neutral. For something to be neutral, it has to have the same amount of positive charge to the same amount of negative charge. Otherwise, it's not, and that's what we call an ion. But we'll look at that later on. So, what he said, what his third point was, electrons surround the nucleus. In the atom's empty space, which is what makes the atom neutral. So if we bring that back, if we bring this piece of information into our visualization over here, we can say that, okay, well, there's randomly floating negative charges, which, okay, when we look at it to scale, are much smaller than the positive charge. So this is what we get. This is Rutherford's model. This is what a visualization of Rutherford's model looks like. And remember, when we usually look at an atom, we see how there's a bunch of circles and orbits, right? Well, the thing with Rutherford's model is that he doesn't talk about orbits. So the model that we're going to look at next, which is Niels Bohr's model, looks at defects and cons in this model of explaining and why this is not as good. And then Niels Bohr gives a much more stronger model, his planetary model. So now let's quickly take a look at that. Okay, now let's look at Niels Bohr's planetary model. But before we do, let's look at why it was needed. What went wrong with Rutherford's model? Because for most of us, it seems that, okay, well, it's a very good model, it's logical, it makes sense, there's evidence as well, the goldfoil experiment. But what is wrong? Well, what was wrong with it was the theory. Because if the electrons revolved around the nucleus, they must lose energy, and therefore collapse into the nucleus. However, this does not happen, because if that did happen, we wouldn't be here. And so everything would be unstable if the electron was to lose energy and collapse into the nucleus. Well, to combat this, Niels Bohr came up with two key postulates, and these postulates are basically rules. So the first rule that Niels Bohr came up with is that only certain orbits, known as discrete orbits, of electrons are allowed inside the atom. And discrete orbits are a key scientific term. Okay, so let's say if I have an atom, let's create a visualization for this as well. Let's make one over here. Let's say this is the space that I'm giving to my atom. This is the nucleus. Remember, nucleus is only just a positively charged ball, protons. It's protons. There's no neutrons. We haven't discovered neutrons yet. So this is my positively charged ball, and it says only certain orbits known as discrete orbits are allowed inside an atom. So let's create some discrete orbits. There we go. Only these orbits are allowed inside an atom for the electron. Okay, so we know that. Now let's look at the second postulate. So we've created discrete orbits within the space that we've given for our atom. And so there's electrons in them. So let's draw our electrons. And remember, the number of electrons that an atom has does not decide what atom it is. It's the number of protons. If the number of electrons varies, that only can tell you if that atom is an ion or not. The number of atoms has no impact on the element. And the next thing, okay, so jumping back, the next thing that Niels Bohr said is that while revolving in these discrete orbits, the electrons do not lose energy. So, in these discrete orbits, while they revolve, they're not losing any energy. Now, I know you may ask, okay, well, oh, what's the proof? He just made it up. Well, it's really complicated. There's these shell numbers K, L, M, N, and then there's orbits, and it's just really complicated if we go into the details of it. So for now, we can just stick with this model and say discrete orbits, electrons do not lose energy, hence they cannot go unstable, hence they cannot. So yeah, so for now, let's just say that electrons revolve in discrete orbits. In these discrete orbits, they do not lose any energy, and if they do not lose any energy, they don't collapse into the proton, and if they don't collapse into the proton, everything does not become unstable, everything remains stable. Okay? But something that these electrons can do is that they can jump. And a key thing to remember is that they can jump between these shells, right? This can go down, this can go up, but that is based upon the energy that they have. So for example, electrons that are further away, so let's say I have an electron in the third shell. So this is the third shell. This is the first shell, this is the second shell, that's the third shell. Okay? So electrons orbiting outermost have the most energy, right? Electrons here are medium energy. These electrons, since they're the most innermost electrons, they're going to have the least amount of energy. So if an electron gains energy, it will jump to the shell with the higher number, and if an electron loses energy, it's going to go one down. So yeah, electrons can jump between these definite paths, but they can't stay, according to this model, they can't stay anywhere in between. So you can't have an electron between the second shell and the third shell. That's not possible. Okay, so after Niels Bohr's planetary model came Erwin Schrödinger's quantum mechanical model. But before that, I think it's very important to recognize another key scientist on the way, James Chadwick. Now, what did he do? James Chadwick came up with the neutron in 1932. Okay? So if someone asks you about James Chadwick, say James Chadwick discovered the neutron. Discovered the neutron. A subatomic particle. Now, what does subatomic mean? So, imagine this is our atom. Now, in that atom, we right now know it can be divided into. So, after James Chadwick's neutron, we know it can be divided into three. We get a proton, we get a neutron, we get an electron. You get these three subatomic particles. Now, these are referred to as subatomic because you have the atom, which they say is the smallest piece of matter, which it is, and then you can divide that atom into subatomic subcategories, so electrons, neutrons, protons. So that's what subatomic means. A subatomic particle with the mass of a proton, with the mass of a proton and zero charge. Okay, so now that we are on the topic of, quickly copy that down. Okay, so, and if you didn't get to copy that down, you can always just pause it. Anyway, now that we're on the topic of subatomic particles, I might give you a quick breakdown of that, and then we'll look at Erwin Schrödinger's model. Now, I don't want to go into too much detail about Erwin Schrödinger's model, because I don't think I can explain it, so I'll just tell you what I know. But before that, let's look at subatomic particles. So we know that there's three subatomic particles. The electron, the neutron, and the proton, yeah? Okay. And these are the two categories we're going to be comparing them. So, the electron is the negatively charged subatomic particle. So it would have a charge of -1. Neutron, discovered by James Chadwick, he said that it's a subatomic particle with no charge, so 0. Proton, positively charged, +1. Okay? Now mass. So when we talk about mass, we're going to look at it in terms of the electron. In terms of the electron. Okay? So the mass of one electron in terms of electrons is 1. Now the mass of a neutron, so how many electrons would you need to equate to the mass of a neutron, is 1,800, and the same with a proton. So although an electron and the proton have the same charge, the proton is much more heavier than the electron. So this is just something to keep in mind. And if you are doing electricity, this is also why we usually talk about electrons flowing through a wire, because they're much smaller than protons. Hence, it's much easier for them to flow, for them to be the charge that flows through wires rather than protons. Because if protons flow through wires, and that's not energetically favorable, you'd rather have electrons flowing than protons going, because protons are much bigger. Okay, now let's look at Erwin Schrödinger's model. Okay, this one's a bit this is the one I can't really elaborate on because it's too complicated. So I'll just give you, just keywords and key concepts for this. So Schrödinger stated that electrons are a probability wave. Okay, it is impossible to know their exact location. Exact location, but however, we can have clouds of probability. Of probability called orbitals. In which it is likely to find the electron. Okay, so visual representation, this is really difficult to give a visual representation of, because of course there's so many components to it, but I'll try my best. So you have your nucleus, and this time it's not just positive charge, it's not just a proton, it's not just a bunch of protons, there's also neutrons. So neutral, positive. Okay, so this is my atom. Okay, and so the electrons are not in any orbitals, they're not in planetary, they're not surrounded, they're just probability waves. So something like this. Now, you see this, right? You see this area over here. This area has less, since this area has smaller probability waves, it's less likely to find an electron over here. However, if you come over here, this area has more probability waves, so you're more likely, so you're less likely here, and you're more likely to find an electron in this portion rather than that portion. But the thing is, we can never be sure where the electron is, and so yeah, it's very complicated, and there's lots of aspects to the last model. But ideally, this is what we want to know. Schrodinger stated that electrons are a probability wave. It is impossible to know their exact location. However, we can have clouds of probability called orbitals in which it is likely to find the electron. So in this area, so this is, and coming back to the planetary model, remember, if this was a positively charged nucleus, we'd have different orbitals, right? It's similar with the Schrodinger model. So let's just imagine that this is our nucleus, and then we're likely to find an electron over here, and then jump here, not so likely, and then we're likely to find electrons over here. And so this kind of compares to how we can find electrons in this area and this area, but it's just probability. So it's not as discrete as Niels Bohr's model, and yeah, this is the most accepted one. So we've went from all these different models, from just a ball to introducing charges with Thomson's Plum pudding, looking at orbitals, how electrons surround them rather than being sat on top, and then finally electrons are waves now, probability waves. They exist in probability waves. So that's how the atom has evolved over time. That's how these theories came and they went, and some were accepted, some aspects were taken, some aspects were ditched because they were not as strong. And so yeah, that's it. If you like this video, well, I'm happy, because now you can get some good studying done. Other than that, if you'd like to see more, just tell me, leave comments down below. If you have any questions, also leave comments down below, and I'll catch you in the next one. Till then, keep studying.